Hello, everybody, and welcome to MME 2305 Material and Energy Balances. I was going to work out a problem I call the lump of coal problem. And this is an actual picture of last year's Christmas present to me, a lump of so-called dirty coal. It's kind of a big deal, and I think it's actually becoming less and less of a deal. I read, I think earlier this week, that 2019 was the first year on record that energy derived from renewable resources such as photovoltaics, so solar panel and windmills, actually surpassed coal production. But coal is still there and people are still using it. I don't know for how much longer society is going to be using coal, but as long as we use coal, we have to pay attention to things like clean versus dirty coal. And all coal is dirty to some degree because you have a carbon footprint associated with it. What makes coal dirtier is the presence of other impurities, and the impurities are generally nitrogen and sulfur. There's other stuff in there though. There's a whole slew of small elements, or small trace amount of elements, and they're heavy metals. But when you have a small trace of element, heavy metal, for example, in this lump of coal, and you're burning a whole bunch of it in a giant power plant, even these trace elements become an issue. I'm going to take a look at dirty coal from the point of view of energy production because we're doing reactive energy balances, and so I kind of find it's pertinent to the discussion and the stuff we're talking about in class lately. So we have our problem, we have our lump of coal, my Christmas present from last year, and we're going to just deal with the impurity of sulfur in our coal. And so we have chemical equations for combusting carbon and sulfur are seen below. So just carbon plus oxygen yields CO2 gas, and sulfur plus oxygen yields SO2. And so these are our two combustion equations that we're gonna care about. We have this kind of information we're given. So if the heat of formation for carbon dioxide is this value, so negative 393,509 joules per mole, and the heat of combustion of sulfur dioxide is negative 296,814 joules per mole. Okay, this is a poorly written question, I'm realizing. You have two lumps of coal, each 1 kilogram. So what is the difference in the heat released between combusting a lump that is 100% carbon compared to one that is 75% carbon and 25% sulfur? So our carbon and sulfur coal is dirty coal. We can recall now that the molecular weight of carbon is 12 and the molecular weight of sulfur is 32. And I probably should have called this atomic weight. And for each one, I won't go back and edit it and hide my mistake. I'm human. So let's carry on, shall we? I left another mistake here. Oops. So there's some animations to follow. To solve this problem, we're going to be using Hess's law because we were given heats of formation on the previous slide. So Hess's law again, we're going to get the energy in terms of the heat of reaction, which is really the heat of combustion in this case. And so it's the heat of formation of products minus the heat of formation of the reactants. And so we're pretty old hands at that. So this is a multi-step process to get to the answer. And hopefully by now you know what step one usually is. And step one is, my daughter's screaming, don't know if you heard that. But step one is find the number of moles. And so our basis is 1 kilogram. 1 kilogram is of course 100 grams. And so our basis is 1 kilogram. So for our lump of coal that's 100% carbon, we have straight up 100 grams of carbon. We're going to convert that to moles, and so 1 mole of carbon gives us 12 grams based on the atomic weight or atomic mass, and so that's 83.3 moles of carbon. And let's see, what's step 2? Step 2 is find the energy in joules per mole, and we're going to find this energy based on the heat of reaction. This time we're not dealing with sensible heats in this one. We're using Hess's law for this equation. So carbon plus oxygen yields CO2. I left it out, but I'll go ahead and verbally say it. The heats of formation for these two elements is going to be 0. So the heat of reaction is simply the heat of formation of carbon dioxide, which is negative 393,509 joules per mole. So that's step 2. We found energy in joules per mole using Hess's law. Now step 3 is find the energy in joules, okay? Because we want to know how much energy is going to be released by this lump of coal. So we find the energy in joules, and we do that by multiplying our heat of reaction, our heat of combustion in this case, which was easily found because 2 of these components ended up being equal to 0. So we multiply this heat of reaction by the number of moles of carbon. Remember, the amount of energy released has to do with the amount of substance releasing energy. So we're multiplying negative 393,509,000 joules per mole times 83.3 moles of carbon, which we found here, and we get a whopping number. So this is, I'll say it in scientific notation, 3.2 times 10, or 3.27 times 10 to the 7 joules negative, so it's exothermic. And so that's some energy there in 1 lump of coal. Pretty interesting. The second lump of coal is our dirty coal. And so again, we have a multi-step problem. Again, the first step is finding the number of moles. In this case, we want to find the number of moles for each component because now we have 75% carbon and 25% sulfur. So we figure out how many moles of carbon are in this lump of coal, and in this case it's 750 grams because our basis was 1 kilogram, so 1 kilogram is 1,000 grams. We multiply that by our atomic mass of carbon to get the number of moles per carbon, just like we did on the previous sequence. So 62.5 moles of carbon. Again, our basis is 1 kilogram again, and we have 25% sulfur now, so that gives us 250 grams of sulfur, and that gives us a total number of moles of sulfur of 7.81 moles of sulfur. Hooray! So now we have 62.5 moles of carbon, 7.81 moles of sulfur. The second step is find the energy in joules per mole. What I did here is I still kept things broken up in 2 components. This is a coal made up of carbon and sulfur, and so I calculated again the heat of reaction or the heat of combustion for the combustion of carbon, and CO2 is really the only thing we care about because carbon and oxygen are 0. So that gives us negative 393,509 joules per mole. Similarly with sulfur, the heat of formation for sulfur and the heat of formation of oxygen is also 0, so we really only care about the heat of formation of SO2, or sulfur dioxide, and that's negative 296,814 joules per mole. I've kept it in separate components just to kind of make it easier because I kept the mole calculation in separate components as well, and at the very end we'll sum everything up because the total delta H is always going to equal the sum of all the delta H's involved in a process, whether it's something we're going in a loop or whatever. So anyhow, we've split it up into 2 components. Step 3 is find the energy in joules, and so I first found the energy in joules per carbon, for carbon, and so it's this value here, and how many, it's a lot, it's like 24 million, if I can look, my eyes are bad. Uncomfortable pause. Yes, 24 million, 23 million for the sulfur component. And then you add all the energy together, and then we get this amount. So this is, I'm just going to say 2.7 times 10 to the 7 joules. So the total energy of this dirty coal is actually a bit less. So let's take a look on the next slide. We'll compare the two. All right, so for our clean coal, we actually have something growing in it. That's nice. I got roughly 3.2, and I probably should have rounded it up, but 3.2 times 10 to the 7 joules. And on this carbon, we had 2.7 times 10 to the 7 joules, or negative 2.7 times 10 to the 7 joules. What that means is our dirty coal will produce roughly 16% less energy. So two reasons not to use dirty coal. One, it creates more pollution, more environmental problems. Also, it's producing less energy. And we kind of saw this when or maybe we haven't seen this yet. Interesting. I'm thinking in my brain, I probably shouldn't do this when I'm recording. If you have gas mixtures, and we saw gas mixtures, how impure gases take more oxygen, they also produce less energy. So that's something else to consider as well. Hopefully this was informative, and hopefully you got the step-by-step into using or calculating energy produced by the combustion of clean and dirty coal. Thank you for your time. Oh my. It's the end of the lecture. If you have any questions, you can email me at drobertson@utep.edu.